Alrighty. Good morning, everybody. Welcome back to Calc 1. The plan for today is we are going to finish off Standard 13 by looking at one more problem. And then you're going to start Standard 14, looking at linearization. I've got my usual office hours for the next couple days. Today at 11 and 2, tomorrow at 10 and at 1. And as far as homework goes, on Friday we will have a Standard 13 quiz. Also, don't forget that homework 16 is due Friday. Before I jump back into motion problems, I want to talk a little bit about courses for next semester. Because this is something I typically do in each of my classes. So, you all are in Calc 1. Probably guess what math class comes next. Calc 2. So should you take Calc 2 or not? I think the answer to should you take Calc 2 generally comes down to yes if you're planning on doing anything sciencey. It's like if you're planning on going on and like doing like a minor in something like chemistry or biology or physics or yes even math. Or also something like econ, I think. Going on and taking Calc 2 would probably be a good choice. So Calc 2 is basically going to pick up where we leave the semester off, looking at more complicated formulas for how do you integrate, talk through things, what are some things you can do with integrals, how can you look at different coordinate systems, and also what happens when you add together infinitely many things. How do you take infinite sums? So the sort of questions you can look at in Calc 2 are like this. Suppose I want to walk out this door from this point. I have to walk halfway to the door first before I can get to the door, right? So I'm going to walk halfway to the door. Before I get out this door, I have to walk halfway to the door. Before I walk out this door, I have to walk halfway to the door. Before I walk out this door, I have to walk halfway to the door. And in general, I have to repeat this process infinitely many times. I have to infinitely many times walk halfway through the door in order to be able to actually walk out the door. So if I have to walk this infinite amount of halfway to the doorness, it should be impossible for me to ever actually reach the door, right? Surprise, I can still reach the door in a finite amount of time, even though I have to walk halfway to the door infinitely many times in the process. So these are the sorts of questions we look at in Calc 2. Like, how does what I just talked about have anything to do with calculus? Turns out there's a lot of cool applications going on there. If you have any questions about if Calc 2 is probably a good fit for you, I'd be happy to talk outside of class. But with that in mind, let's do some math. By the way, this circle, I heard several of you were marking on as it came in, that is a good circle, which is why you know it wasn't drawn by me. It's a leftover from yesterday. You can draw a circle like that using a compass. This is a chalk compass. And the idea is you put this one down, and then the chalk piece, do like this, boop. And look, a perfect circle. So you know it wasn't drawn. And sadly, it's taking up way too much space, so it has to go. So when we left off last class, we were looking at motion problems involving position/distance traveled, velocity, and acceleration. Where if s of t is the position or net distance traveled, the recall from last class, we said that in order to go from position traveled, if we were to differentiate this function, we would get a formula for velocity t. And if we were to differentiate again, taking s double prime of t, or v prime of t, we're going to get a function that tells us the acceleration of a moving object. And so what I'd like to do today is to take a look at this last problem in the packet, where once again we're shooting a cannon on Earth, and we want to shoot it at a castle this time. We're no longer pirates, we are now, I don't know, medieval soldiers or something. There's also a problem about Wile E. Coyote, and I love Wile E. Coyote and Roadrunner. We're going to skip that one for now. Encourage you to try that one out as a bonus problem, practice problem. And the idea here is that in this example we're looking at with the cannon on Earth, we're given three pieces of information. That vertical acceleration of the cannonball due to gravity is going to be negative 32 feet per second squared, just like it always is on Earth. We also know that the cannon is being shot from ground level, and that the terrain is flat. And finally, we know that the shots are going to land 5 seconds after being fired. And our question that I'd like to answer is, what is the initial velocity of our cannonballs after being fired? So let's take a look at this. This is a somewhat similar setup to the problem we were looking at in the second half of class yesterday, where we were given a formula for acceleration and given a couple of initial values. And we were basically asked to find information about v of t and or s of t given our formula for a of t, the acceleration function. So right off the bat, I want to do the same thing we did at the start of yesterday's problem, which is this first line I think is pretty self-explanatory. It's a formula for acceleration. But I'd like to take a look at these second and third lines and see if we can write this in terms of formulas. Being able to say, if the cannon is shot from ground level, that means one of these three functions, s of t, v of t, a of t, at some particular value of t has to be equal to some particular number. So how can we take this information that the cannon is shot from ground level and write that as a formula involving one of these three functions? When?
S of 0 is equal to 0.
Why s of 0 and not v of 0?
Well, because the cannon is shot from ground level, so that's your position. And at time equals 0, the cannon is on the ground, so it hasn't traveled any distance upward.
Yeah, so this piece of information right here, the fact that the cannon is shot from ground level, is going to tell us that if we were to sort of graph the height of our cannonball as time goes on, it's going to start with a height of 0, and then it'll probably shoot upwards and then go until it hits the ground. We're going to assume that the castle is at ground level, that the castle is at a height of 0. So I agree with you, Wen. I think that we could rewrite this second equation here as being s of 0 is equal to 0. Meaning we're not firing from the top of a cliff. I don't know, maybe we should be. We could probably do more damage to the castle. But the fact that it's shot from ground level means that our initial height is going to be 0. How about this third one? That the shots are going to land 5 seconds after being fired. And when we say land, what we mean is we're going to assume that it hits the castle over here, that the castle is at ground level, and that that's going to happen at t equals 5 seconds. Zach?
V of 5 equals 0.
V of 5 equals 0. So you're saying that when the shots hit the castle, they're traveling with a velocity of 0?
Something like that. I don't know. Probably not. Never mind. Scratch that. That's wrong.
Zach has shown a lack of confidence in his answer. I don't think we want to say that V of 5 is 0, because that would be implying that when the cannonballs hit the castle, the cannonball is not moving at all. And I would say it's probably not going to be the case when it hits the castle. If it's hitting the castle, it's probably doing so while moving. Hopefully pretty fast, or it's not, or it may just bounce off the castle and be a pretty crummy cannonball if that's the case. So I don't think this last line is going to tell us that V of 5 is equal to 0. Josh?
You could use S of 5 and find the position of it when it lands, and then figure out with that your distance per feet per second, maybe.
Yeah. I think instead of saying something about V of 5, I think this third equation, bullet point is actually telling us something about S of 5. Specifically, that S of 5 is equal to 0. That just like how the cannonball started out at a height of 0 at time t equals 0, at time t equals 5, it's also going to have a height of 0 because that's when the cannonball is landing. Probably with a positive initial velocity, probably with a positive or negative, actually negative, because it's going to be coming downwards on the castle. With a non-zero velocity at time t equals 5, because cannonball is actually hitting the castle and not just kind of floating there in front of the castle all menacing. So that would be kind of terrifying to see cannonballs floating there. And so here's our 3 pieces of information. A of t is negative 32, S of 0 equals 0, and S of 5 is equal to 0. So in other words, at this point in time right here, t equals 5 is going to kind of be the end of our parabola that's traveled. Initial velocity of the cannonball. So what expression are we actually hoping to find? Someone other than this corner over here.
I know.
Dr. Keebler and his loud conversations. So if we're looking for initial velocity, what could that be? Avery?
V of 0.
Yeah, I think what we want to find is what is V of 0. In other words, if we take the tangent line to our function here, at time t equals 0, we want to know what the slope of that tangent line is at V of 0. So we have a couple initial values. We have a formula for A of t, and we know what we're trying to find. We're trying to find V of 0. V of 0 specifically, Avery, what makes you say V of 0 and not V of some other point in time?
This is initial velocity.
Yeah, initial velocity, where initial almost always, pretty much always means at time 0. When it's starting off, as we're firing the cannon. Okay, so I think we can start off with an approach similar to what we did in the end of class on Monday. We can take our function of acceleration, that our A of t is negative 32. And how can we take our acceleration function and use it to find a formula for velocity? In other words, what do we have to do to go from acceleration to velocity? Ellen?
You'd have to integrate, so it'd be negative 32x plus c.
We're going to be integrating this negative 32. And so we'll get negative 32,
T plus t.
negative 32t plus some constant c. Okay. Since we're doing this in terms of time, I want to stick with the variable t here. So we have a general formula for our v of t, that it's going to be negative 32t plus c. So now, just like last time, we can use an initial value for velocity in order to help us find what c should be equal to. So what value given to us in the problem can we use in order to solve for c?
At the midpoint, so at the apex, the velocity is going to be 0. Or
At this point right here?
yes,
Okay, where does that occur?
halfway, so it's be 2.5.
I don't know.
You're not wrong. But that's not the approach I wanted to take for this one.
Sorry.
No, that's perfect. No, that's perfectly okay, and that's a good idea. Say, aha, since we're firing from ground level and landing on ground level, halfway in between is going to be the point where we have a velocity of 0.
Yeah. So at 2.5 t, the velocity equals 0.
This is not wrong, but I want to see if we can find a different way to do it, because what you just said wouldn't work if, say, we were firing from an initial height of, I don't know, up here somewhere.
Okay.
We were firing from above. That would work in this specific example, in other words, but it's not very generalizable to, what if these two heights at time t equals 0 and t equals 5 were not exactly the same. But yeah, that's a good idea. Zach?
Integrate that again, get s of t, but you're gonna get negative 16t squared plus ct plus 0, because you already know s of 0 equals 0. And then from there, you're gonna put 5 in. And then,
All right, I'm going to stop you here before you just solve the rest of the problem on the fly. Yeah, so we have a problem here, and that last time we were given an initial value for velocity that we could plug in to solve for our constant c here. But if you look, we're given two initial values, but neither of them are for velocity. They're both for position. So, Zach, I think what you proposed is we can't actually plug in anything to v of t right now, unless we want to be really sneaky and use Hannah's approach. So instead, Zach, what you proposed, correct me if I'm wrong, is that we integrate a second time. All right, let's do that. So we're going to go ahead and integrate this without actually solving for c first. So if we do that, we'll get an integral of negative 32t plus c, taken with respect to t. And someone outside this front corner here, just if you can answer if you'd like, what are we going to get if we integrate negative 32t plus a constant c? Rachel?
It would be negative 16 squared plus
ct plus another c? Hush, you're right, but we're not there yet. I'm gonna give it another variable named d, because potentially these two constants don't have to be the exact same constant. The constant we get from integrating acceleration doesn't necessarily have to equal the constant we get from integrating velocity. So I'm going to use different variable names for this constant and this constant. And so now what we end up with is we end up with a formula for our position function that has two unknown constants in it. that S of t is equal to negative 16t squared plus some constant times t plus a different constant. And so our goal is going to be to solve not only for the variable c here, but it'd probably be good to also solve for the variable d as well. So and so we now somehow need to use both of our initial conditions, the fact that s of 0 equals 0 and that s of 5 is equal to 0, to help us solve for both c and d. Or the reason why we have two different unknown constants here is the fact that we couldn't solve for c back at the v of t stage. Now that plus c term is kind of getting carried over to a plus ct term in our position function. So to start off with, how can we solve for c and or d?
You could plug in s of 0 first to cancel out the 16t squared and the ct. So you solve for d first, and then you could plug in s of 5 to solve for c.
Okay, so Zach, I think this is what you were basically saying. You wanted to, you're jumping the gun a little bit, but you wanted to say that if we plug in 0 for t, it should come out to 0, and so we could use that to solve for our constant there at the end.
Not that one. Because so that's a 0, you already know that'd be d. Because if the t, they both have t, so when t is equal to 0, that's just going to cancel out 0, so then you already know what d is.
Yeah, that's what I meant.
Oh, okay, yeah.
Yeah, so we could say that since s of 0 equals 0, I agree with Josh / Zach with the two of you proposed. If we plug that in, we'll get s of 0 is negative 16 times 0 squared, is up with the chalk, plus c times 0 plus d is 0. And then if we solve for d, bye-bye, bye-bye, we're going to get that d is equal to 0. So we could use our first initial condition, the fact that s of 0 equals 0 is going to tell us that d has to be equal to 0. So our s of t we can now write as being negative 16t squared plus some constant times t. Let's get someone from these two columns. What can we do if we want to solve for c now? We were able to solve for d using this s of 0 equals 0 condition, but plugging in 0 for t and setting that equal to 0 didn't help us to actually find the constant c at all. Vera?
We can plug in 5 for t and solve for s of 5 equals 0.
See, now you want to use our other initial condition, that s of 5 is equal to 0, to see if we can solve for c. I think that one will work out a little nicer, to get c at least. So if we do that, we'll get s of 5 is equal to negative 16 times 5 squared plus c times 5 should be equal to 0. All right, negative 16 times 5, that is negative 80, times another 5 is negative 400. So that's going to give us that negative 400 plus 5c is equal to 0. Add 400 to both sides, we'll get that 5c is equal to 400. And if 5c is equal to 400, what is c going to be equal to? Yeah. 400 over 5, which is 80. So ultimately, that's going to then tell us exactly what our s of t is it's going to be equal to negative 16 t squared plus 80t. So unlike last time we were given an initial value for velocity and an initial value for the position function s of t, and we were able to use at this step our initial velocity value to solve for c before integrating the second time. This time through, though, we had to integrate a second time first because both of our initial values were for s of t, and then we were able to plug in both of our initial values, s of 0 equals 0 to solve for d, and s of 5 equals 0 in order to solve for c. We're not quite done yet, though, because the problem wanted us to find not just a formula for position function, but a formula for initial velocity. Or as Avery put it, we want to find what v of 0 is. So how can we go about finding v of 0, given the information we now have? Yeah.
Since c equals 80, you can put it into the v of t function, so negative 32t plus 80.
Oh, okay. Let me see. I think we're done with it. Okay. So we now know that v of t should be, which was negative 32t plus c, we can now say is negative 32t plus 80.
Yes. And then the initial time is 0, so you can put 0 in for t. And so v of 0 is 80.
So v of 0 is negative 32 times 0 plus 80, which is going to give us 80.
Miles per hour. Or what is it in? Feet per second.
Yeah, since acceleration is feet per second squared, I think we're going to have feet per second for our velocity. 80 miles per hour would be a pretty terrifying cannonball.
Yeah, that'd be psychotic, bro.
Yeah, that'd be psychotic, bro. All right, Hannah, since you suggested it earlier, and I hadn't thought of doing this approach, I want to see what happens if we use your idea of set velocity equal to 0 at the halfway point at t equals 2.5.
Yeah.
I'm just curious to see what happens when we do that now.
Okay.
Okay, so Hannah's approach was saying v of the halfway point should be equal to 0. Maybe shouldn't. So what was our v? It was negative 32t plus c. So if we have negative 32 times 2.5 plus c is equal to 0. Negative 32 times 2.5. All right, that's going to be equal to negative 16 times 5. We divide negative 32 by 2 and multiply 2.5 by 2. So this will give us that negative 80 plus c is equal to 0. Which would give us c equals 80. And it turns out, Anna, with your approach, we wouldn't even need to integrate a second time. We would just get c equals 80, and then plug in v of 0 to get negative 32 times 0 plus 80 is 80 feet per second. So that's actually kind of a slick method you came up with, that I really like. Noticing that if at time t equals 0 and time t equals 5 are both going to be with a height of 0, then the apex of the parabola should be exactly halfway in between at 2.5. But for the record, if we had started with an initial height, say up here, and this was our trajectory, we couldn't have done this approach because we wouldn't have known at what point is the apex of the parabola going to be because it wouldn't have started at, because it wouldn't be nice and symmetric where 0 and 5 are the same height. But for this particular problem, that was kind of a slick way to look at it. Nice approach, Anna. So sometimes, depending on the information you're given, you might have to integrate twice before solving for either of your constants. So in this case, without Hannah's trick available, we had to integrate a of t to get v of t, and then v of t a second time to get s of t, and then use both of our initial conditions for s of t to solve for the two different constant terms we got, rather than being able to solve for the constants one at a time, like we did in the example at the end of class on Monday. Any questions or comments about what we just did? All right, in that case, that is going to do it for standard 13. We're going to move on to standard 14. For standard 14, we're going to learn how to think like calculators. Already doing it? So if I were to ask you, for instance, what's the square root of 4.2, you'll be able to just go, processing, square root of 4.2 is blah.
Something like that.
That's really cool. I'm impressed. A broken calculator. I think it's like a fruit.
I can only add square root of 4.2.
Square root of negative 4.2 does not exist.
What's the Arbalist? No, that's not Abacus. That's what I am. The same with the beads.
You are.
All right, so here's the scoop. I'm going to look at the function f of x equals square root of x to start with. And as I asked Josh, I'm going to know what square root of 4.2 is equal to. Dr. Urstel, square root of 4.2 isn't a nice number. You're right, it is, dare I say, irrational. Irrational meaning it's not something that can be written as a nice fraction.
2.147.
2.147? No.
Close.
No. So, square root of 4.2 is not a nice number, but when we plug square root of 4.2 into a calculator, it knows what to do, and it gives us the first 10 digits after the decimal for whatever that comes out to. It's going to be an infinite decimal, by the way. How does a calculator know that? Josh, you say you're a calculator. How do you know that?
It's a little guy in there that just does it.
Little guy in there does it. All right. How does a little guy in your calculator do that?
They keep where else. They just kind of do it. They just make the cookies. We don't know how.
Magic goes into it. We don't know how, but there's magic involved. I mean, it's actually
Coding.
coding. What kind of coding?
Advanced coding.
I'm about to tell you a dirty little secret about calculators. If you type square root of, I don't care how advanced a calculator you use, you plug square root of 4.2 into a calculator, it's not going to know how to evaluate that exactly. Instead, what a calculator does is it does a bunch of sneaky math behind the scenes, and it gives you an approximation. It says square root of 4.2 is approximately equal to 2 point, all right, Zach. It's one packet. It's approximately equal to 2.0494, and then it'll give you probably a few more digits that I didn't write down.
I forgot it was a 071.
How embarrassing.
That happens.
But what the calculator does behind the scenes is it does a bunch of sneaky methods to try and approximate what square root of 4.2 is. And it depends on what your calculator is for how advanced the methods are. But there's an entire branch of mathematics called numerical analysis that's all about how do you approximate things like square root of 4.2 that are kind of impossible to calculate out exactly. And we're going to be looking at a method that actually uses the derivative function to say, how could we come up with an approximation for square root of 4.2 using, say, some information about the derivative of the square root function. Specifically, what we're going to be doing is we're going to be looking at a point like, I don't know, square root of 4. And we're going to be looking in this standard at how do we actually find a formula for the tangent line to this function at a point like 4. We'll call this L of x here in a minute. So we're going to shelve the question of what is square root of 4.2 for just a second and look at how do we find a tangent line to the square root function at x equals 4. So, what information do we need if we want to find an equation for a line? It's a high school algebra type question. If I want to find a formula for this line right here, what sorts of information could we use in order to help us find that formula potentially? In other words, if we look at the formula for a line, like y equals mx plus b, what are these values m and b that we can speak of in order to get formulas?
Y-intercept.
Ooh, what's the y-intercept? We could say that b is going to be the y-intercept. In other words, the y-coordinate of this line at x equals 0. And Helen, what about this m value?
That would be the slope.
That would be the slope. Yeah. So if we know what the slope of our line is, and we know the y value at x equals 0, the y-intercept, we can plug these into the slope-intercept form of the line and get y equals, say, 2x plus 5 or negative 6x plus 4. Get a nice formula for a line that way. If we want to take the tangent line to the square root function at x equals 4, how can we find the slope of that line? Rachel? Yeah, by definition, we know what the slope of the tangent line is at x equals 4. The slope of the tangent line should just be equal to f prime of 4. That's how we originally defined the derivative in the first place. If you think way back to standard 4, we said that the derivative of a function at, say, 4 is going to be the slope of the tangent line to that function at x equals 4. So the slope is just going to be f prime of 4. So let's find that. If f of x equals the square root of x, what is f prime of x going to be equal to? Now we're looking at a standard 5 type question. How would we differentiate the square root function? When?
1 over 2 square root x.
1 over 2 square root of x. Wow, how did you get that, other than remembering it?
Oh, well, that's power rule and then technically chain rule. So you can rewrite it as x to the 1/2, pull down the 1/2 front, and subtract 1 from the exponent. So it'll be 1/2 x to the negative 1/2.
Yeah, which is the same as 1 over 2 square root of x. I like it. I don't think we necessarily need to use the chain rule at all for this. But by rewriting square root as something, taking something to the 1/2, we can use the power rule to find what our f prime is. And so if f prime of x is 1 over 2 square root of x, that's going to tell us that f prime of 4 is going to be equal to 1 over 2 square root of 4. And it's time to start calling on people. Mackenzie, what is 1 over 2 square root of 4 going to come out to? Yeah, it's going to come out to 1 over 2 times 2, which is 1/4. So we know one piece of information about our tangent line. It's going to have a slope of positive 1/4, which we found by just taking the derivative, f prime of x, and plugging in x equals 4. By definition, f prime of 4 is just the slope of the tangent line to our function at x equals 4. So we know something about our slope now. It's going to be a 4. We still don't know what our y-intercept is going to be. And to be honest, I don't think finding the y-intercept will be particularly easy in this example. So instead of using slope-intercept form of our line, I'm going to use another form of a line that maybe Riley remembers.
That y equals m times x minus h plus k.
Y equals m times x minus h plus k. Ooh. That's a similar sort of form. That's not going to be quite what we use, but actually that is going to be what we use. I'm going to write it slightly differently though. Josh?
Is point slope?
Point slope form is what I have in mind, which I think, Riley, is essentially what you were describing, just written slightly differently. Where the point slope form of a line is if you know the slope of your line, if slope equals m and x naught y naught is a point on your line, you could say that the line has formula y minus y naught equals m times x minus x naught. So in other words, if you know maybe the slope of your line, which we do, we found that the slope just came out to a 4. And if you can find some point x naught comma y naught on your line, then the formula for your line is going to be given by y minus y naught equals your slope times x minus x naught. So something I would like to do is to find so since we already know the slope of our tangent line, if we can find some point on our line, some x naught comma y naught, that'll give us a point on the line or on the tangent line, we can use that to then put our line in point slope form. And then once we have it in point slope form, we can put it in y equals mx plus b form if we like. So I'd like to find a point on this line. Rachel, you have any ideas for how we could find a point?
4, 2.
4 comma 2. Why is 4 comma 2 a point on that line? It's a point on the line because it's the point?
Because at x equals 4, if you plug it into the equation, you would get y equals 2.
Ooh, okay, so if you take square root of, so if you take f of 4, you get 2. I certainly believe that, square root of 4 is 2. And here you're using the fact that at x equals 4, the tangent line and the function are going to be at the exact same y coordinate. I like it. Yeah, so what Rachel's proposed is that at x equals 4, we know the y coordinate of this point on the function. We could say that f of 4 is going to be equal to 2. Square root of 4 is 2. And so, since the tangent line and the original function f of x are equal at x equals 4, since 4, 2 is a point on the original function, it's also going to be a point on our tangent line. So let's write some of that down. Since 4 comma f of 4 equals 4, 2 is a point on f of x at x equals 4, since the tangent line and f of x are equal at that one point at x equals 4, equal meaning they take on the same y value, four comma 2 should also be a point on our graph of on our tangent line. And if you notice, this only works at the point x equals 4 itself. We couldn't find our tangent line at 0 by plugging in f of 0, for instance, because f of x and the tangent line don't have the same y value at 0. Or at x equals 5, they're different from each other, or any other values of x, really. But at the point x equals 4 itself, since we're taking the tangent line at 4, the y value of our tangent line at 4 will be equal to the y value of our original function, square root of x, at that point specifically. So in other words, moral of the story is, I agree with you, Rachel. I think 4 comma 2 is a nice point on our tangent line that we'll be able to use to plug into the point slope formula. Any questions or comments about that? Let's write that down. So let's plug that in. So we have a point on our tangent line. Our point is 4 comma 2. We have our slope. Our slope is a 4th. So if we plug that information into the point slope formula, y minus y naught equals m times x minus x naught, we'll get a formula of y minus 2. Well, I'll just write it out here so it's kind of clear where it comes from. So our x naught comma y naught is going to be the point 4 comma 2. Our slope is going to be our m value of a 4th. So if we plug in all those values, we'll get that our tangent line has a formula of y minus 2 is equal to 1/4 times x minus 4. Where here, I just replaced x naught and y naught with the x and y coordinates of the point on our tangent line that Rachel found, 4 comma 2. And then the m I replaced with a 4th, corresponding to the fact that we know the slope of our tangent line should just be f prime of 4. And now we can solve this for y, and we'll get that y is equal to 1/4 times x minus 4 plus 2. And Riley, I think this is kind of the form that you were talking about earlier. Y equals m times x minus h plus k. Here, if we replace h with 4, k with 2, and m with a 4th, that would be what you were describing. And if we multiply this out, we'll get 1/4 x minus 1 plus 2. And so our tangent line is going to be 1/4 x plus 1, I think. Turns out our y-intercept is at 1. Any questions or comments about how we found this formula for L of x? Oops, spoiler alert, we're going to call it L of x. So we found a formula for our tangent line. You can write it as L of x equals 1/4 x plus 1. Dr. Gerstle, I thought we were trying to find square root of 4.2. What's up with this tangent line approximation thingy? Here's the sneaky part. If you notice, our tangent line, L of x, and our original function, f of x, at x equals 4.2, these are not equal. They're not going to have the same y value, but the y values that they're going to have are really close to each other.
So what if it was something slightly greater, like 4.5 or 4.6? Would we just then plug in, so at 0.5, just like pick kind of the closest point to it, so it's close enough?
The general idea is going to be pick a point that's as close as you can get. That's something you know how to take the square root of. All right, Mr. Calculator, you know what the square root of 5 is? It's not real. I don't either. So I probably wouldn't use square root of 5 because that's not a nice number. But I'd probably still use square root of 4 and say, this is probably not going to be as accurate as we want. But this is the best I got. I'm going to rely on my calculator to know more advanced methods than this. And by my calculator, I mean me. We'll get to that. That's a good question, though. We're going to actually get to that probably next class before we kind of fully answer the question you just asked. So before we actually approximate what square root of 4.2 is, I want to give us a definition, which is the idea of linearization. Scary L word I've written on the board. Where the idea of linearization is that the linearization of f of x at x equals a is basically just going to be the function that gives us the tangent line to f of x at that point. Is the function L of x defining the tangent line at x equals a. And it's going to have a formula of L of x is equal to f of a plus f prime of a times x minus a. So, in other words, if you plug everything into this formula, it'll give you a formula for the tangent line to a function f of x at x equals a. 1/4 x plus 1. Okay, I wrote that down, so I can erase it. So you might be wondering, Dr. Gerstle, what is up with this formula? Where does it come from? So the idea behind where does this formula come from? It comes from actually using the point slope formula of a line. Specifically, actually, the version of it, Riley, that you proposed earlier. Just moving the plus k term up in front of the m times x minus h. Where you're going to ask the question of why does this formula work? It comes down to the fact that we know that the tangent line at x equals a to f of x is going to have a slope equal to f prime of a. So in other words, our slope is f prime of a. That's just by definition. The slope of the tangent line is what the derivative is equal to. According to what Rachel said earlier, we can always find a point on our tangent line by just saying, oh, a comma f of a. Just like 4 comma f of 4. And the example we looked at was a point on our graph. And a point, x naught comma y naught, is just equal to a comma f of a. Since at x equals a itself, the original function f of x and our tangent line are always going to have the same y value, that just being whatever f of a is. Thus, with point slope formula, y minus y naught is equal to m times x minus x naught. We're going to get, if we replace our slope in the point slope formula with f prime of a, we'll get f prime of a here. X naught and y naught we can just replace with the x and y coordinates of our point on the graph of our tangent line, which is just going to be a comma f of a. So if x naught comma y naught is a comma f of a, then we can replace y naught with f of a, and x naught with just plain old a. And now, if we just add f of a to both sides of this equation, we'll get that y is equal to f of a plus f prime of a times x minus a. And this y we could then replace with our functional notation of L of x. So if you ever want to find the tangent line to a function f of x at a point a, you can use this formula. Find f of a, f prime of a, plug these into this equation, and that'll actually tell you what's the tangent line to your function at that point. All right, we're finally ready to approximate f of 4.2. In other words, square root of 4.2. So what we need to do to actually approximate what square root of 4.2 is going to be equal to is, well, by definition, we know square root of 4.2 is equal to f of 4.2. If f of x is the square root function, then plugging 4.2 into f means it'll be taking the square root of it. If you notice, f of 4.2 is really close to this y coordinate here, L of 4.2. Because at x equals 4.2, our square root function and the tangent line function, L of x, are going to be really, really close to each other. They're equal at x equals 4, so at numbers close to 4, like 4.2, f of x and L of x are going to be, they're not going to be exactly equal, but they're going to be pretty close to each other. So instead of finding the square root of 4.2, in other words, what f of 4.2 is, I'm going to approximate it and say that f of 4.2 is going to be really, really close to L of 4.2. Because these two y coordinates, the y coordinate of this point and that point, are going to be very close to each other. So instead of trying to take the square root of 4.2, which is hard, what we can do instead is plug 4.2 into our linearization function, L of x, and instead take 1/4 times 4.2 plus 1. Which to me looks evaluating this expression looks a heck of a lot easier than trying to evaluate whatever square root of 4.2 is. Because if we want to plug in 4.2 into this, we'll get 1/4 times 4.2. So that's going to be half of 2.1, which will be 1.05. And I'm going to get 2.05. So that we're not finding an exact number for square root of 4.2, because the exact square root of 4.2 will be some infinite decimal, goes on forever. But we could say, let's find L of 4.2 instead, because taking the square root of a number, that's hard. Plugging a number into a line, 1/4 x plus 1, that's relatively easy. To a calculator, plugging something into 1/4 x plus 1 is child's play. For you, it might take a little bit of work, but the idea is taking a number, multiplying by a constant like a fourth, and then adding 1 to it. To a calculator, those are pretty easy steps to do. Josh, you could have done that in your sleep by now. He's not one to brag.
Stay home.
Stay healthy. Just for fun, I actually found what square root of 4.2 is earlier using a computer. And the actual square root of 4.2 is about 2.0494 ... It goes on forever. Let's see. John, what do you think? Did our tangent line approximation 2.05 give us something pretty close to the actual answer?
Yeah.
Looks like it to me. If you ask me, are 2.05 and 2.0494 blah 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 close to each other? I would say, yeah, these are pretty close to each other. So, the idea behind using a linearization to do math like a calculator is to do something like this. Square root of 4.2 is hard. Let's find the tangent line at a nearby point and use the tangent line to approximate the original value we want to find. And use the fact that L of 4.2 is a heck of a lot easier to calculate than F of 4.2. And then that gave us a value 2.05 that was pretty dang close to our actual answer, 2.0494. One last question. What if we had used this tangent line to try and approximate square root of 17? If we had plugged in x equals 17 into our linearization, we would have gotten L of 17 is 1/4 times 17 plus 1, which is 4 1/4 plus 1 is 5.25. Whereas if we plug in f of 17, we plug in square root of 17 into the square root function, that's going to give us about 4.123. Good try that. Follow-up question. I don't know, Emily. Do you feel like our tangent line at x equals 17 gave us a good approximation of 5.25 to the actual square root of 17? No? Why do you say no?
Because we're using the tangent line at 4.
And because these two numbers are not really very close to each other. Like these are like 0.001 away from each other. Whereas these two numbers are like over a full unit apart, it's like 1.13 from each other. So something to think about for next time. Why was this approximation so good, but this approximation was pretty bad? I'll let you stew on that, and then we'll come back on Friday, and after the quiz, we will talk a little bit more about why was one approximation pretty effective and one approximation not so good. See y'all on Friday.